Coming in hot with the Euclidean geometry, I need to complete the statement. Opposite angles of a cyclic quadrilateral are. Now, they're testing a certain theorem. They're asking, do you know that the opposite angles of a cyclic quad add up to 180? And there is a shorter way to say that. We can say that they are supplementary. And a nice way to remember it is like there's a hidden S in 180 degrees. So if angles add up to 180 degrees, we say that the angles are supplementary. And another nice nugget of information is if they are complementary, they add up to 90 degrees. And there's a hidden C in the 90 degrees. So in summary, the opposite angles of a cyclic quadrilateral are supplementary because they add up to 180 degrees. Okay, getting to the juicy questions. This angle is 25, that's been indicated there. O is the center, that's quite important. These points are on the circumference, and then first up I need to get D1. So D1 is over here. And D1 is touching a very special line. There's a sneaky weasel alert, but there's a radius on the loose. Again, I see another radius, which is going to make an isosceles triangle. So the base angles of an isosceles triangle are going to be equal for the following theorem. So if you have an isosceles triangle that has equal sides, you can conclude that the angles that are opposite the equal sides are equal. And your reason is angles op equal sides. So we're just going to say D1 equals 25 degrees for this reason. And your 1 mark comes from the statement and reason. And bear in mind, there's another reason you can use. I can say angles op equal radii. That's also acceptable. And next up, I need the size of O1. So I can see that O1 is an exterior angle of the following triangle. Triangle DOC. If I just extend this line DO, it encompasses the angle O1 between the triangle and that line extension. So we're going to use the following theorem. Exterior angle of triangle. And how it works is to get the exterior angle, you go to the opposite interior angles and you add them together and it gives you this exterior one. So applied in the context of this question, the opposite two angles are these 25s. So I add those together to get O1. And let's quickly go through how we're going to write that up. So O1 is going to be equal to 25 plus 25 for the reason of exterior angle of a triangle. And 25 plus 25 will just give me 50, my bro. And yeah, let's have a look where the marks come from. So you're going to get 1 mark for your statement and then 1 mark for your whale all reason. Next up, I need to get the size of A1. Okay, A1's in quite an abstract place. So how we're going to start off is we look at A1 and we follow it backwards to its chord or arc. So if I have a look at A1 and I look at the 2 lines that A1 is touching, I'm going to follow those 2 lines backwards and even more backwards until I get to the circumference, and it takes me to this imaginary chord. And then once I've identified my chord, I follow it down and down again, and it takes me to O1, to the center of the circle. So now I know that A1 and O1 are subtended by the same chord, and you can also see it as the same arc. And this would be the arc that I'm referring to, BC. But I prefer the chord, it just makes more sense to my brain. And to get the physical size of A1, we're going to use the following theorem. Angle at center is 2 times the angle at circumference, which states that the angle at the center is always 2 times the size of the angle at the circumference, provided they're subtended by the same chord or arc. So the one at the center is always bigger, so A1 will be half the size of O1. And we're going to write up our statement just like this. A1 equals half the size of O1, which is 50. And our reason is angle at center equals 2 times angle at circumference. And then half of 50 gives me a toasty little 25 baht. And your first mark will come from the statement, second mark will come from the reason. And if your brain is better at recognizing shapes, this does form like a bow tie of a shape sometimes. I find that a little bit unreliable because it's not always a bow tie. And there's also a different way we could have approached this question. I could have used angles in the same segment with this bow tie. But this bow tie, all 4 points are on the circumference. With the previous bow tie, 3 points are on the circumference and 1 is at the center. And that's kind of why I don't like getting used to the bow tie for angle at center equals 2 times the angle at circumference, because you can confuse it with the bow tie, which is angles in the same seg. And lastly, we come full circle with this question. We need to get the angle E. Now, if I look at the angle E, it is nested inside of a cyclic quad, my bro. So what do we know about cyclic quads? We know that the opposite angles add up to 180. So these two angles will add up to 180, my bro. And that's going to form our statement, and we're going to clap this oak as our reason. So our statement will read as follows. E1 plus 25 is equal to 180 because of op angles of cyclic quad. Sorry, that should just be an E, not an E1. And then we're going to yoink that 25 over. It becomes minus 25. And 180 minus 25 should give me 155. But don't be naughty, don't take chances. Clap that in the calculator, press equals, and your search agrees. Yes. And your first mark comes from the correct reason. Second mark comes from the correct statement. And just another little nugget of information before I go. You could have used this cyclic quad and you would have got to the same outcome. In this video, we're going to focus on getting the length of lines with Euclidean geometry. Okay, so they've given us a whole bunch of information here. Let's get that marked off on our sketch. Yeah, it's much better. And now we are asked to calculate the radius of the circle. We can see it sitting over there. And I so desperately want to do Pythag in this triangle, but I need another side to pull that off. So we're going to come here to this 12 units, and we're going to use a Euclidean geometry theorem. And that Euclidean geometry theorem is line from center perpendicular to the chord. If you have a line from the center that is perpendicular, aka 90 degrees to the chord, it's going to cut my chord in 2 equal parts, aka bisect it. So I know that AE is the same length as EB for this reason here. Line from center, perpendicular to chord. And we're going to state it just like this. AE equals EB, line from center, perpendicular to chord. And then if this is 12 units, I'm just going to halve that to get the length of both of these sides. So if I halve that, it gives me 6 units. So now you can see I've set myself up for the Pythagoras spot. And the Pythagoras theorem states that your hypotenuse squared is equal to the sum of the other two sides squared. So the hypotenuse over here. To identify it, your right angle just points at it. So you see this right angle here, it points at the hypotenuse, so the hypotenuse is R. So I'm going to switch out this H to an R. And then in A's place, I can literally put any one of them. I'll just put the 5. And in B's place, I'll put the other side, which is the 6. Again, we do not take chances here. We pump that in, press equals, and we get 61. And then all that's left to do here is to get rid of that square. And I'm going to accomplish that by square rooting both sides. And then I'm just left with the radius to be the square root of 61. And they do want the answer in third form, so I'm going to leave it just like that. And then I'll slap a little units there, and then I'm officially done. And quickly having a look where these 4 marks come from. We get 1 mark for this statement, 1 mark for this reason, 1 mark for the Pythagoras statement, and then our answer as a third form gets us our last and final mark here. And in 5.2, we've been asked to calculate the value of x. Now x is over there, it's in a completely different triangle. So we've got to somehow start working with this triangle. And I just know the length of one side of that triangle. So let's see what we can do. So if I have a look at this triangle, this side over here, CO, it's a sneaky weasel, my bro. There's a radius alert. He's on the loot. So we know that the length of CO is root 61 units because it's radius. This is also a radius and we know its length. So let's see how we state that. So we're just going to say OC is the same size as OA because they are both radii, and we just slap on the physical size next to that of root 61 units. Now I'm ever so close to getting x. I can use this triangle, but there is a problem. I want to apply Pythag over here, but I can't because I don't see a 90-degree angle. So I'm going to have to use the following Euclidean theorem to bring that 90-degree angle into the picture. So it's called line from center to midpoint from chord. If I've got a line coming from the center that goes to the midpoint of this chord, aka the chord is bisected, then I can conclude that this little angle here is 90 degrees. So we can see that happening here. We've got a line from the center that goes to the midpoint of the chord CD. I know it's the midpoint because of these two little lines over there. So we know that F1 is 90 degrees for this reason. Line from center to midpoint of chord. And now that I've got the 90 degrees in my triangle, I can clap some Pythagoras. But right, so let's get the Pythagoras theorem going. Okay, so the hypotenuse squared. So the 90 degrees points at the hypotenuse. So I'm going to replace it with the root of 61. Okay, and then I can put any one of these two sides into A's place. So I think I'll just put the x in there. And then the last side will have to go into B's place. So I'm going to put the 7 inside of B's place. And now the mission is to solve for x. So root 61 squared is just 61. The square and the root cancel out with one another. And as always, if you're not too sure, just triple check it with your calculator and yeah, you'll see number 1. And 7 squared will give me 49. And then I'm going to take that 49 over to the other side of the equation. And it becomes minus 49. And 61 minus 49, I believe that's 12. And it most definitely is 12. Triple check yourself. And now we just need to get rid of that square. And we're going to get that done by square rooting both sides. And then we're going to pop that into our calculator. So if I pop it in, press equals, it gives me 2 root 3. So I can list my answer like that, or I can hit the S to D and list my answer to 2 decimal places. And just make sure whichever one you list, you clap the word units next to it. But so let's have a look where the 3 marks come from. First mark comes from telling me that F1 is 90. Second mark comes from the reason for that. And the last mark comes from the statement for Pythagoras. In question 6, we've been given the following diagram and we're told PQ is a tangent, this is a cyclic quad, and we've got a couple of straight lines, and these 2 lines are parallel, quite important. Then we need to prove that A is equal to B2. So I can start with any one of these 2 angles, but before I do that, let's glamify our sketch a little bit, but yes, it's nice, bro. Okay, so I'm going to start off with B2. So B2 is located over here, and I want to follow it back to its chord. So if we look at B2, we look at the 2 lines touching B2, line BD and BC, and we follow it back. And we follow it back some more, and we get to the chord DC. And I know a sneaky theorem with a chord and a tangent, but the tan chord theorem. And that theorem goes a little something like this. The angle between the tangent and the chord will be equal to the angle that that chord subtends. And remember, it works both ways. I can use this angle between the tangent and the chord and follow that down to get this angle. So over here, I know that angle C1 will be equal to B2 because B2 is subtended by this chord, and the angle between the chord and the tangent will be equal to that angle. So I know that C1 is a red angle. And we are going to state it just like this. B2 equals C1 due to the tan chord theorem. Now I'm going to focus on C1 and see what I can do with C1, maybe try relate it to A somehow. So if I have a look at those two angles, I can see like both of them are touching the parallel lines. So I can apply my parallel line theorems. And I see some alternating angles, but I see the Z. Can you see it, my bro? So A1 will be the same size as C for alternating angles. And to briefly run through that theorem, if the lines are parallel, then like these angles in the armpits of the Z or the N will be equal. So I know that C1 will be equal to A, and this will be my reason, alt angles, and then we've just got to modify the parallel lines to suit ours. So ours will be line AB is parallel to PQ. So let's get that written down. And we just stated like this, angle A is equal to angle C1, because the alt angles, semicolon AB parallel to PQ. Next up, we can see that B2 equals C1, and A is equal to C1. If they equal to the same thing, they have to be the same size. So B2 is equal to A. And then you don't really have to put a reason for that line. If you do want to put a reason, you can tell me like they both equal to C1. And then we're going to quickly run through where the 4 marks come from in this question. So we get 1 mark a pop for each statement. And then we get 1 mark a pop for each wee little reason. And now we have to prove that D3 is the same size as D1. So I'm going to choose one of these angles to start with. I think I'm going to choose D1 because I can see that that's an exterior angle of a cyclic quad. And I know a theorem that deals with the exterior angle of a cyclic quad. And that theorem goes a little something like this. The exterior angle of a cyclic quad will be equal to the opposite interior angle of the cyclic quad. So if we apply that here, this exterior angle of the cyclic quad, I follow it across to the opposite interior angle. So it's going to be equal to the whole of B over here. So let's get that written up. And we just write it up like this. D1 equals B1 plus B2 exterior angle of cyclic quad. Now I'm going to see what I can do with this orange angle. And look what that orange angle is touching. It's touching a parallel line. So I can do a Z with that orange angle. Alternating angles, my bro. And to show you that a little bit more visually, we can see the Z over there. And the alternating angles will be equal. So we're going to write that up just like this. C3 is equal to B1 plus B2. Alt angles, and that's because line AB is parallel to the line PQ. And now I'm going to have a look at this orange angle and see what I can do with it. And if I look at this orange angle, it's touching a tangent and it's touching a chord. So I'm going to follow that chord up and up again, and we get a winner chicken dinner. We get to D3. So D3 is also an orange angle. Okay, so let's state that. And we utilize that theorem in the previous question. It's the tan chord theorem, and we say that C3 is equal to D3 because of the tan chord theorem. Now we're going to start with our conclusion. So firstly, we need to make the link between these two angles. Because D1 and C3 equal the same thing, they both equal B1 plus B2, we're going to state that they are equal to one another. And if you would like, you can mention the reason that they both equal B1 plus B2. And then we see that C3 equals D1, C3 equals D3, and C3 also equals D1. So it stands to reason that these two have to be the same. So we're just going to hit a therefore D1 equals D3, and we've adequately proved what they are asking us to do. So let's have a look where the 5 marks come from. First mark comes from your statement. Second mark comes for your reason with the exterior angle of cyclic quad. The third mark comes from the statements and reason with the alternating angles. And then the fourth and fifth mark come from the tan chord theorem with its statement and reason. Okay, welcome to your challenge round. Okay, we've been given a whole bunch of information here. And now the question is asking us to prove that this is a cyclic quad. Now there are three ways to prove a cyclic quad, and let's go through them quickly. So I've got converse op angles of cyclic quad. If I prove that the opposite angles add up to 180, then I've got a cyclic quad. If I prove that the angles inside of a bow tie are equal, then I've got a cyclic quad because of converse angles in the same segment. And if I prove that the exterior angle is equal to the opposite interior angle, then I can conclude I've got a cyclic quad because of converse exterior angle of cyclic quad. Now I believe it's going to be this one, and let me show you why. It's because we kind of already know what one of the exterior angles of the cyclic quad is. It's y. But it doesn't always unfold that way, so we've got to kind of see where it takes us. So let's keep that in the back of our mind. It is a loose guideline on what to do. So let's get started, mark off our information and see what we can do. Yes, nice, bro. Okay, so we're going to mark off y with blue angles. We're going to mark off x's with like this yellow angle. And we've got a tangent over here. Alright, and I'm seeing something. X is in between a tangent and a chord, my butt. We've seen this theorem like 6 billion times in this paper already. It's the tan chord theorem. Okay, so we look at the other line that x is touching. It's touching the line DE, which will be our chord, and then we follow that chord down and down again, and it takes us to an angle that's equal to x. So now we know that C equals x due to the tan chord theorem. And now if I have a look, I can see x and y are inside of a triangle. Triangle DEC. And if I just extend the line EC, then we can see we've got an exterior angle of this triangle formed by E2 plus E3. Now E2 plus E3 will be equal to the opposite interior angles added together for the following reason. Exterior angle of a triangle. To get the exterior angle, you go to the opposite interior angles and add them together. So this whole angle here will be x plus y. So it stands to reason that E3 must be the same size as y. And it's a little bit tricky to write that up, so I'm going to walk through that quickly. So let's have a look at what we're going to say first. We're firstly going to say D1 plus C equals E2 plus E3 exterior angle of triangle. And once we've got that written down, we know that D1 is y, and we know that C is x. We proved that in the previous question. So we're just going to swap these to an x and a y like so. And then we're going to state that E2 is the same size as x. They told that to us in the question. And now we're going to jump to the conclusion that E3 has to equal y. And just for this line over here, you can put given as your reason. And then another nice way to imagine it. So imagine I change this to an x. So x plus E3 equals x plus y. So it stands to reason that E3 has to equal y. And now I'm going to direct my focus towards this y over here. I can see it's touching this line, which is equal to this line, so it's inside of an isosceles triangle. And in an isosceles triangle, we always know that the base angles are equal, my bro. And that's for the following theorem. Angles op equal sides. If I look at the equal sides and I go to the angles that are opposite them, the angles will be equal. So now we know that B1 plus B2 will equal y. And we're going to write it up just like this. Angle B1 plus B2 is equal to E3, and both of those are equal to y, and we knew that because of angles op equal sides. And now our job is almost done. Look what we've accomplished. We've proved that the exterior angle of the cyclic, or exterior angle of this quadrilateral, is equal to the opposite interior angle. So now it is a cyclic quad. We've proved it. But there's a couple of things we need to state. We're not home safe just yet. So, firstly, I've got to make the link between this angle and this angle. So I'm going to hit a therefore D1 equals B1 plus B2, just like this. And I knew that those two angles are equal because I went and proved that they are both equal to y. They both have a value of whatever y is, in a sense. And now we can copy paste this. ABED is a cyclic quad. And after we state that, we went down this avenue to prove it. That the exterior angle is equal to the opposite interior angle. So we're going to slap this down as our reason, exterior angle of cyclic quad. And then we've officially waxed this question, my bro. So let's have a look where the 16 billion marks come from. Your first mark comes from the statement and reason with the tan chord theorem. Exterior angles of a triangle, that reason gets you a mark. Stating that E3 is y gets you the third mark. Doing the isosceles triangle property, angles of equal sides, gets you the fourth mark. Concluding that these two are equal gets you the fifth mark. And the last mark comes from the statement and reason that wraps up this question. In question 8.1, we've got two circles. We've also got a parallelogram in the mix. And we have a tangent over here to the smaller circle. And with all that, we need to prove that AD is the same size as DE. So, let's talk about how we're going to do that. If we have a look at those two sides, we can see they're sitting quite snug inside of a triangle. So if I prove that this angle, E1, is equal to this angle A, then that will successfully prove it's an isosceles triangle, and I can conclude that ED will be the same size as AD. Okay, now let's see how we're going to get that done. So I'm going to start off with one of the angles. It doesn't matter which one you start with. I'll just start with A. Now I can see that A is sitting inside of that parallelogram they were talking about. And a certain theorem with the parallelogram states that the opposite angles are equal inside of a parallelogram. So if I look at A and go to the opposite angle here to C, I know that that's going to be a green angle for this reason, op angles of par. So we're going to write it up just like this, angle A equals C, op angles of par. Now I'm going to see what I can do with this green angle. See if I can relate it to E1 somehow. Okay, and then what I'm noticing is that C is sitting inside of a cyclic quad. Yes, would you look at that? So if I just extend this line EB a little, then I can see that E1 is an exterior angle of that cyclic quad. And we know a theorem that relates the exterior angle to the interior opposite angle. It's exterior angle of cyclic quad, which we've seen in this paper quite a bit before. So now I know that this angle C will be equal to E1, and we're almost home safe. So let's get that written up. We're just going to say C equals E1, and then we're going to slap this next to that as our reason. And after we've stated that, we're now going to revisit the triangle we spoke about earlier to wrap this question up. So I firstly need to make the link between these two angles. So we can see they both equal C, so therefore these two have to equal. And we're going to state it just like that. And now we're going to jump into our conclusion. So I'm going to show you the theorem that helps us conclude that AD is equal to DE. It's called sides op equal angles. So how it works is, if you know that angles are equal inside of a triangle, you go to the opposite sides in those triangle, and you know that they're equal. So now if I go to the opposite side AD, if I go to the opposite side ED, I know that they're equal for this reason. And we write it up just like this. AD equals ED, sides op equal angles. And what I like to remember is, if I'm like concluding that the sides are equal, that's going to be the first word in my reason. And now I've done what they've asked for. It doesn't matter if the order of these letters are switched around, it still means the same thing. And your 4 marks, first one comes from the statement and reason with a parallelogram. Second one comes from the statement, third one comes from the reason with the cyclic quad, and the last one comes from this Euler reason. In question 8.2, we're going to need to prove that DC is equal to BG. So let's get that marked off a little bit more clearly. I need to prove that these two lines are equal in length. And we're going to start off by looking at DC. Now, if you remember, DC is actually part of a parallelogram. And I know a property of a parallelogram with the opposite sides, which is that the opposite sides are equal. So if you've got a parallelogram, this side is equal in length to this side, and this side is equal in length to this side. So now I know that DC will be the same length as BA for this reason, opposites of a palm. Sorry, can you please pass the palm? The Parmesan cheese, bro. And we're going to write that up just like this. DC is equal to AB, opposites of palm. So now, if this length is the same as that length, I just need to prove that this line is equal to that line, and then by default this line will be equal to that line, because they'll all have the same length. And now these two lines are sitting inside of a triangle, and if I prove this triangle is an isosceles triangle, then I can prove that this length is the same as that length. So what that will entail is that proving the base angles are the same. So I need to kind of get G to be a green angle. And if I prove that G is a green angle, then I can conclude these are the same length. So this will have the same length as that, etc., etc. Now let's see how we're going to do that. So I'm going to look at the two lines touching the angle G, and I'm going to follow them backwards some more, and they're going to take me to this imaginary chord. And then from that chord, I'll go up and up some more, and it takes me to C. So I can apply angles in the same segment. It's the bow tie. He's back, my bro. If you want to see the bow tie, it's over there. Quite a classy little gentleman. Okay, so we're going to conclude that angle C's angle is equal to angle G for this reason. Angles in the same seg. And with that out the way, we're going to revisit this triangle we focused on earlier. Now I've got to make the link between G and A. So I've got to state that those angles are equal. So we just write A is equal to G. If you want, you can slap a reason there. So you see how we proved that A is equal to C in the previous question. So we can just say that they both equal to C. Because if you look in this line, G is equal to C. In the previous question, A is equal to C. So both G and A equal to C. So it stands to reason that A and G have to be equal. We've been doing that on our sketch by saying like they're all green angles. Okay, now we can start to cook a little bit. Now, sides op equal angles. So we saw this theorem in the previous question. If I've got equal angles at the base of my isosceles triangles, then the sides opposite them must be equal. So if I see my base angles are equal over here, I'll go to the opposite side, which is BG. And over here, I go to the opposite side, which is AB. And I can conclude they're equal for this reason. And we're going to state it just like this. AB equals BG, sides op equal angles. Now we're almost there. Can you see that AB is equal to BG? And AB is also equal to DC. So it stands to reason that DC must be equal to BG. They all three of the sides have the same length. And we have officially waxed this question. So having a look where the 16 billion marks come from. Your statement and reason saying the op sides of the palm are equal gets you your first mark. The statement and reason get you 1 mark a pop for doing that bow tie that we discussed earlier. And then your 5th mark comes from concluding these sides are equal using sides op equal angles. That reason gets you the last mark. And that officially wraps up this vraagstel, Machana Bean.